Do 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 do. Do, 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 do. Okay, welcome to iChem, and we are in our discussion of heat and temperature. And so the next thing we want to talk about, we talked all about temp, we all talked all about heat, we talked about Q equals MC sub P delta T, and we want to get into this idea of phase changes and latent heats and heating curves. So let us talk about, or let us consider this question. Consider sublimation. Yeah, so let us consider sublimation. What is the opposite of sublimation? Egads. Sublimation. Well, I think we need to learn something here, don't you? Yes, I do too. So let's talk about phase changes, yeah? Turn and face the changes, right? With phase changes. So what is a phase change? Let's talk about our definition. What's a phase change? Phase changes are easy. They are changes of state. That's what phase changes are, right? Not going from Indiana to Illinois, but changes of state, such as, we can talk about types here, right? Such as what? I can go from a solid to a liquid. That's a phase change. And what do we call that when I go from solid to a liquid? We call that fusion in chemistry, or we might also call it what? Melting. Good. I can go from a liquid to a gas, and that would be what? Vaporizing. Vaporization. Vaporization, we'll call it vaporization. I could go from what? Solid to a gas. Now, we're not always too familiar with this. This is called sublimation. Got it? And you guys are familiar with solid to gas. Dry ice, when you buy some dry ice and it automatically goes from the ice form to the gas form, that is sublimation. Good. And then I can go the other directions, right? I can go from a liquid to a solid. And what is that? When we go from a liquid to a solid, we call that freezing. And I can go from a gas to a liquid, and that is called condensation. Condensation. And I can go from a gas to a solid, right? And that is what we call deposition. Depositing. Deposition. All right. Great. So, solid to liquid, that is fusion, melting, liquid to gas, vaporization, solid to gas, sublimation, liquid to solid, freezing, gas to liquid, condensation, and gas to solid, deposition. Do we have enough to answer our question? All right, sublimation. What is the opposite of sublimation? Cool. Well, sublimation is going from a solid to a gas. So what's the opposite of that? Gas going to a solid, and we call that what? Deposition. Okay, is sublimation exothermic or endothermic? Okay, I remember exothermic. That means what? Heat is released. And I remember endothermic. That means what? Heat is absorbed. Okay, so that means I need to go back and we need to add some stuff. Which of these are exothermic or endothermic? Going from solid to liquid, what do you think? Do I need to put energy into that or take energy out? Well, for me to go from a solid to a liquid, what do we have to do? We usually have to heat that up. So that means that requires energy. So that means that is energy is absorbed. That is endothermic. What about going from a liquid to a gas? We have a liquid on the stove, right? We have to boil it. We have to vaporize it. That requires us putting the heat to it. So that's endothermic. And going from a solid to a gas, that is also endothermic. And all these others are going to be just the opposite, right? Going from a solid to a liquid is exothermic. Going from a gas to a liquid is exothermic. And going from a solid to a gas, going from a gas to a solid is exothermic. Wow, have you ever really thought about that one? Going from a liquid to a solid is exothermic. So just remember, next time you're outside and it's really cold out, right? And you're freezing, what do you want to do? You want to get a big gallon of water, and let's say it's like 5 degrees below Celsius, really cold, right? And so what's going to happen? This water is going to start crystallizing and becoming a solid. It's going to go from liquid to solid, meaning it's going to freeze. But freezing is what? Exothermic. So that means when it freezes, heat will come off of that, and then you can get warm by putting your hands over that hot steam, well, not steam, coming off, that heat coming off of the liquid that is freezing. Now, is it really exothermic? Yeah, it's exothermic, but you think you're really going to stay warm enough? No, you're not going to stay warm enough. You're still going to be unhappy because it's still really cold outside. Just a fascinating thought. All right, is sublimation exothermic or endothermic? Okay, I'm going from a solid to a gas. That means what? Heat has to go in here, so that means it is endothermic. Heat is required. Heat is absorbed in the process. Yahoo! Great. Condensation. You guys try this. Condensation. What is condensation? Condensation is going from a gas to a liquid, right? So what's the opposite of that? Going from a liquid to a gas, and that is called what? Vaporization. Yahoo! Vaporization is oh wait, did I answer that question right? So yes, I did answer that one right. Good. Is condensation exothermic or endothermic? Okay, I'm going from a gas to a liquid. I'm going from a higher energy state to a lower energy state, you'll learn, and this is exothermic, right? Going from a gas to a liquid. Going from a liquid to a gas, right? That's like boiling stuff on the stove. I have to put heat into it, so that's endothermic. So the opposite of that must be exothermic. There we go. Perfecto. Next. Consider the latent heat. Latent heat. Consider the latent heat of vaporization for water. If delta H vap for water equals 2.26 kilojoules per gram, what is the latent heat of condensation? I think we need to learn something about heats in relationship to phase changes. So we want to come down here and we want to learn about latent heats. Okay, latent heats. Okay, now do you recall when we were talking about heat in general last time, we said, hey, Q is equal to M C sub P delta T, right? Well, let me tell you, unfortunately, this does not work, yoink, for phase changes. Nope, Q equals M delta C sub P delta D doesn't work. And why is that? Because in phase changes, guess what? Delta T is equal to 0 for phase changes. And we'll get into that a little bit later. And so that thing would be 0, which would mean Q is always 0, but that's not the case. There is an amount of heat required for a phase change, or heat liberated in a phase change. And so we have these things called latent heats. Latent heats. And that is essentially the heat of a phase change. The heat either gained or lost during a phase change. And we use as a symbol delta H, change in enthalpy, to represent our latent heat. And we have 6 latent heats. Can you believe that? I have delta H fusion, which would be what? The latent heat of fusion. I have delta H vaporization, which would be the latent heat of vaporization. And that's what? How much heat This is how much heat is necessary for melting, how much heat is necessary for vaporization. Of course, then I would have delta H sublimation, which is the latent heat of sublimation, which is what? The amount of heat necessary to cause sublimation. And then I would have delta H freezing, which is the latent heat of freezing, which is the heat released. This is the heat released when something freezes. I would have the delta H of condensation, which is equal to the latent heat of condensation or condensing, and that is what? The amount of heat released when something condenses. Remember, these guys over here are going to be released because they're exothermic. These guys over here are going to be energy absorbed because they're all endothermic. And then delta H, what? Deposition is equal to the latent heat of deposition. And that is the amount of heat which is released when something deposits, when something goes from gas to a solid. And there's a relationship between all of these. And here's what it is. The heat of fusion is equal to negative heat of freezing. The heat of vaporization is equal to the negative heat of condensation, and the heat of sublimation is equal to the negative heat of deposition. All right, you guys have all of that? Cool. And by the way, these guys here, since they are exothermic, their delta H's are always going to be less than 0. That's the convention, that the end result has less energy in it than the beginning result, so the change in heat is going to be negative. These dudes over here, because they're endothermic, their delta H's, their latent heats are always going to be positive. Woo! Got it. Wow, lots of stuff here already. Cool. Here we go. So we have the latent heat of vaporization for water. All right, I understand that now. And it is 2.26 kilojoules per gram. What is the latent heat of condensation? Okay, what did we learn? We said that delta H vaporization is equal to negative delta H condensation. So the same amount of heat that goes into, that causes vaporization, is released when condensation occurs. And so if 2.26 is equal to that, then my delta H condensation is equal to what? Negative 2.26 kilojoules per gram, meaning when 1 gram of water condenses, 2.26 kilojoules are released. That's what that negative means. That negative means released. Got it? Cool. All right. Let us move on. Let me check the time. Okay, yeah, we can move on. So, here we go. Let's put this all together. Let us consider this heating curve for water. Okay, let's take a look at this for a second. What do we have going on here? All right, here I have temperature. Yeah, and here I am adding heat. So as I go from this direction, if I go in that direction, I am adding heat. Now, where do we start? We start down here at A, right? A is at negative 25 degrees. This is water. So what do we have at negative 25 degrees? We have ice. Okay, so what's going on from point A to point B? Well, I start with ice. I start adding some heat, and what happens as I add heat? My temperature increases. So I add heat. What happens? I am increasing the average kinetic energy of my particles, and as a result, what happens? My temp increases. Okay, that makes complete sense to us, right? Cool. And in this area, I can figure out heat, that my Q associated with this, and we're going to call it Q ice, is going to be equal to M of my ice, C sub P of my ice, delta T of my ice. Good. What's the delta T in this case? We go from what? 25 to, what's this right here? 0. So my delta T on ice in this case would be equal to 0 minus 25, right? Cool. Now, what happens next? We go from B to C. Let's go with a different color. B to C. And notice, as I go from B to C, what happens? Nothing happens. No, something happens. I keep adding heat, right? So I add heat, but what happens to that? There is no change in average kinetic energy. There is no change in temp. Why is that? Because all the heat is used to convert the solid to liquid. I have to, what is that called? I have to cause fusion to occur. So all the heat goes towards fusion. Got it? And what's interesting is the temp does not increase until every bit of that ice has been first converted to liquid. Cool. So now, how do I get Q for fusion? Q for fusion, we use a different calculation, right? I'm going to use my M of my ice times delta H, my latent heat of fusion. Now, later, you might see it in moles. Right now, our information is going to be in mass because for us, our heats of fusion are going to be kilojoules per gram. But sometimes you might see those in kilojoules per mole, and if you do, then you need to multiply it not by the mass of ice, but by moles of ice. Good. Oops. Let's take a look now. What's happening from C to D? Ooh, look at C to D. So I go from C to D, what's happening here? If I go from C to D, I start here. I continue to add heat. What happens? My temperature increases. Good. I go from C to D. Zoink. C to D. What am I doing? As I add heat, what happens? The average kinetic energy of what? Really, now they're liquid, right? Of my liquid particles increases, and what? The temp thus increases, right? Good. And so once again, now I can get a Q, and my Q for my liquid portion is equal to M of my liquid, C sub P of my liquid, delta T of my liquid. Now, I'm not talking about my delta T total. I'm talking about delta T of my liquid. So where's my delta T of my liquid? Well, it starts right here at 0, and it ends right here at 100. So my delta T for water here is equal to 100 minus 0. Got it? And as I'm putting in heat here, the only thing that's happening is I'm exciting my liquid water. It's moving faster. I'm not changing any of that liquid to steam until I get where? When do I start changing that liquid water to gaseous water? When I go from D to E. Let's look at D to E for a second. Zoink, 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 zoink. D to E, what's happening? Look at, I'm adding a whole bunch of heat. Na 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 na. And what happens to the temperature? It doesn't move. Why? What's happening here? Vaporization is happening. All the heat is required for what? All the heat is used to convert that liquid in those particles that are in liquid to particles that are now in the gaseous stage. So we add heat, right? My heat does what? It overcomes what keeps things in the liquid state. It overcomes the IM forces. It may overcome the ionic forces. It may overcome the metallic forces. It all depends on what I have. It may overcome the covalent network. But these forces of attraction, which hold liquid particles close to each other are overcome when I add heat. And I convert then my particles from the liquid state to the gas state, right? And what do we call it when we go from the liquid state to the gas state? We call that vaporization. I am vaporizing my particles. And during that time, what happens to temperature? T remains constant during this, right? Good. So how do I get Q? So Q for my vaporization is going to be equal to mass times my delta H vaporization, or like I say, sometimes you might get moles, and we just have to look at the units, check your units, or moles times delta H vaporization. All depends on units of your delta H. Good. And finally, as I go from E to F, what color? Green again. So I go from E to F. Green looks off on this, doesn't it? That just, maybe it's okay. So if I go from E to F, what happens? As I add energy, what happens? My temperature increases. So I add heat, I add energy. What happens? My average kinetic energy of my gas particles increases, meaning the temp of my gas increases. Got it? And then how do I get Q here? Q of my gas equals M gas C sub P gas delta T gas. Woo, mama! So let's see if we can add some questions. Answer some questions. Why does the temp increase from A to B? Because I am increasing the average kinetic energy of my ice particles. Well, really, of my particles in the solid particles, H2O particles, in the solid state, aka ice, right? Why is the temp constant from B to C? Because I am overcoming forces of attraction, not completely, because I'm just going from the solid state to the liquid state, thus allowing my particles to go from the solid state to liquid state. Got it? And I guess I should be a little more clear here. All heat goes toward overcoming. No heat goes toward increasing average kinetic energy. Cool. Okay, I think that's probably going to be plenty for today. Next time, look at this wonderful question. We are going to figure out the total heat that is required to transform ice to steam. Egads. Okay, that'll take another 25 minutes. See you guys. Hope you have a wonderful day. Ciao.